Okay, so today we will talk about measurement. In quantum mechanics. I want to stress that I will touch only the surface, or only scratch the surface of this topic, which is very deep in some sense, and it touches also with some philosophical kernel of this subject, which has long been debated since the founding fathers put the theory forward. So I will not adventure in touching very sophisticated philosophical questions, which I wouldn't probably be able to really detail to you in the most appropriate way. So let me just give you the few basic things that people tend to accept about what quantum mechanics does, including some objects that look a little bit mysterious, like the collapse of the wave function, the famous collapse of the wave function. Okay? Now, the fact that this theory somehow it's reasonable is confirmed by the fact that it has survived experiments for almost 100 years now. So in some sense, the theory itself doesn't need to be a mathematical theory without, I mean, it is a physical theory, and the ultimate check is experiment. So let me just give you a few things which I think are still important to have clear in your mind. So let me start with the first a remind actually. We have said that important operators are Hermitian operators. And Hermitian operators, which we have seen many, like Hamiltonian, angular momentum, and things like this, are associated to observable, so things that you can measure. Now, one important property of an Hermitian operator obviously in this Hilbert space that we said is the Hilbert space describing really the states of the system. One important property is that an Hermitian operator can be diagonalized, okay? So you can solve, in principle, this problem, phi an equal to an phi an, okay? So this number here is called the eigenvalue of the thing, and the collection of those numbers forms the so-called spectrum of A, okay? For the Hamiltonian, we have seen the eigenvalues and so on. Now, the fact that this is Hermitian immediately allows you, this is a very simple thing that you can prove yourself, that these quantities are real. Okay? Eigenvalues of Hermitian operators are real. Proof. Okay? Now, to be a little bit more general, however, I'm not going to assume that these are non-degenerate. Each one of them might have a certain degeneracy. Okay? For instance, L square, okay, or J square. We have seen that the possible values are J plus 1. However, each value, so for instance, for J equal 1, this is 2H bar square, is not degenerate. It's, in fact, 3 times degenerate, 2J plus 1 in general, okay? So there is a degeneracy in general, and this is quite generic, okay? So I will assume that this is, in general, degenerate with some index I, and I runs from 1 to some number, let me call Dn, is the degeneracy of the eigenvalue An, okay? In the notes I call it Gn, but I think that D somehow suggests the word degeneracy in a better way, okay? Oh, now, sometimes whenever I don't need to specify all these details, I will call this simply n, okay? But if I need to do more sophisticated arguments, maybe I have to spell out that this n is really some label associated which allows me to distinguish the eigenvalue and possibly another label, I, which distinguishes several states, all degenerate with the same eigenvalue. Okay? So just don't be confused if sometimes I write this detailed thing, sometimes I write a more sketchy thing like this. Okay? Also, the spectrum might be discrete, or might be continuous, or might be discrete and continuous. So there is a discrete part and a continuous part. Okay? We have seen this for certain problems, like harmonic oscillator is fully discrete. The Coulomb potential, there is a discrete and a continuous part. Okay? Now, before I proceed with the theory of measurement, let me introduce some formal objects that are quite useful. They are called the projection operator. Now, in three-dimensional space, okay, you know this very well. If I have a vector R, you know that I can project it on the axis. Okay? So every vector R, which has certain components x, y, and z, or in other words, which is x, the unit vector in x component, the unit vector in the y component, and the unit vector in the z component. Okay? Can be projected on one of the axes. What is the projection operator? It simply takes R and associate to it its, for instance, x component. So this piece. Okay? This is a projection on x. This is a projection on y, and this is a projection on z. How do I make the projection? I just take a scalar product, essentially, right? If I take a scalar product with x, this will survive, and this will just be killed. All right? So in the same spirit, if I have a certain basis, okay? So I have to stress once more that this collection of all these objects here form a basis. So phi n is a basis of the Hilbert space. And even more than that, I can always select this basis to be orthonormal. Okay? The fact that two states associated to a different eigenvalue are orthogonal is very simple. Again, prove this. Okay? So not only an are real, but states associated to different an will be automatically orthogonal. On the contrary, the fact that these are automatically orthogonal is not immediate for degenerate eigenvalue. However, you can always construct combinations of degenerate states which are orthogonal, and in the end, the full basis is orthonormal. Okay? So in other words, I do have that phi an I, phi an prime I prime is equal to the delta of n prime and the delta of I prime. Okay? So this is one assumption I'm going to make about the basis of the eigenstates of an Hermitian operator, which I have selected as basis of the Hilbert space. All right. Now, with this thing, I define a projection operator which does the following. When acting on the state n, it gives me essentially 0 if m is different from n, and the same state if m is equal to n. Okay, in this language it would mean if I want to project a state that is already x, for instance this one, then I get 1, projection along x. If I want to project z or y, I get 0. Okay? Is this clear? This is what this thing is telling me, and I can write it with the Kronecker delta in this way. Okay. Now, it's obvious, simple to write matrix element of this. Okay? So if you want to write, for instance, the matrix element n prime of this projection operator Pm is simple to do it, okay? Because you have just to add n prime here. So this would be delta n m delta n prime m, okay? Or if you want equivalently delta n prime. Okay. Now, what is the usefulness of them? For instance, suppose that you have a given state psi. Okay? Now, being this a basis, you can always expand this state on the basis. Okay? So there will be the basis element and some numbers, some complex numbers that allow you to expand psi. Now, you know very well, by a trick that we have already seen, that the way to obtain these numbers is just to take the scalar product with, for instance, suppose that I write this in this way, and I want a certain number, then if I take the scalar product with phi n, then all n prime different from n will just disappear because of the delta. Where is it? The delta here. On the contrary, psi n will just stay there. So, okay, so this sum will be just sum over n prime, psi n prime, phi n prime. This is the delta of n prime, and therefore this is just psi n. Okay? So the coefficient here is just the projection of the state on the element of the basis. Okay? Very well known to all of you. Okay. Now, with this understanding here, so let me return to this simple writing here. With this understanding, it's pretty simple that if you apply the projection operator along M, for instance, to the state psi, what do you get? Well, let me just use this. It's sum over n, psi n. Since this is a linear operator, I can write Pm phi n. But I know that this is just the delta nm times phi n. It's written here. So if I use now the delta, this means that only the m term survives. Okay? So you see, Pm is an object that takes only the m piece of the state. Okay? So the piece staying in the direction, say, m, and lets all the other things to evaporate. Okay? So pretty much like here. Projection on x takes this piece, which is the x part, and lets all the other things go. Is this clear? Now, there is a Dirac way of writing this operator that, let's verify, is the following. Let's see why. If I apply this object, it's a formal thing. You see, it's really a state And to the right of the state, there is a bra. It means, obviously, take the scalar product of anything is to the right. This is the meaning of this object. Until now, we have seen bras only in scalar products, right? But now, if you just extend a little bit this mental thing, you realize that whenever this acts on a state, indeed, you have a scalar product. So it's phi m times phi m psi. Okay? And this scalar product is exactly what we calculated before, is the component of psi on direction m. So it's psi m. Okay? So you see that this is indeed the action of P, as we have stated before. Okay? So you can write either Pm in this way, with the delta Nm there, or in Dirac notation like that. Now, one obvious properties of the projection, you understand it even from this. If you project on a certain direction, and then you do it again, the second time is meaningless, because, I mean, a projection of a projected thing does nothing more than just confirming the projection, right? So the P square, you can prove that Pm applied twice is like Pm applied once only, okay? You can prove this in a very simple way. For instance, let us prove it from the Dirac way of writing. Then on the left, I have phi m applied to phi m. But you see that this is just a way of writing 1, okay? Because the states are normalized, and so this thing is just phi m. Okay? So the square of Pm is just equal to Pm. Okay? If you want to use the other notation, you can still do it. So for instance, apply another P here, okay? You realize that, another Pm, you realize that the first action of Pm already contains only M. So when you apply the second one, nothing more happens, because it's already only that component. All right? Good. Now, look at this expression here. And look at this expression here. This is telling you that the m component, psi m times the state, phi m, is just a projection of the state. Okay? So you can see that this is nothing but the projection of psi on n. So another way of writing this is sum over n of projection Pn applied to psi. Now, when you look at this expression in this way, they are all obvious things. I mean, very simple things. Don't think of any complicated thing. But when you look in this way, you immediately realize that the sum over all possible basis states of the projection is equal to the identity. Okay? So these projections have two very important properties. One is that P square is equal to P, and the other is that they are a so-called resolution of the identity. In the sense that you write something simple like identity as a sum of projections on all possible basis vectors. This is sometimes useful. It looks strange, but it's useful because if you have a scalar product of certain times, you can insert the identity written as a sum of projection. Even better if you use the Dirac notation, you will realize that this provides to you a new way of writing that scalar product. Okay? We'll use it quite often. Okay? Now, once again, all this I have said with a simple index n, but if you are patient enough, you could reinsert all the a, n, and I there. Okay? Okay, let me give you a few examples. Yeah. Yes. Okay. The first thing is that psi is equal to sum over all possible basis vector of a certain coefficient. Then we discover that Pn acting on psi, we wrote it for m really, is equal to exactly this quantity. So what you see here really is Pn psi. Okay? Then I substitute this here, and I realize that psi is equal to sum over n of Pn psi. You see, now this doesn't depend on n. It's again psi. And psi equal to sum operator times psi means that the operator is to be just the identity. Okay? This is the trick. Okay. Yeah. Yes, yes. This is a relationship that holds in the full Hilbert space of infinite dimensions. One should be a little bit careful, however. Not necessarily this spectrum is discrete. Okay? So when I write sum over n, sometimes this should be taken with some flexibility. There could be a continuous part of the spectrum. A piece of the sum becomes an integral over the spectrum. Okay? So the full theory, okay, is rather more delicate because of the presence of a possible continuous spectrum. And the way of writing it necessitates a little bit of care. But if you allow me just a simplified notation with the discrete thing only, this is true even in infinite dimensional space. For instance, for an harmonic oscillator, it would be strictly correct. Okay? There is an infinite Hilbert space, I mean, an infinite number of elements. And in fact, you know that the basis for that state is given by Gaussian multiplying Hermite polynomials. This is a good basis to expand functions in minus infinity plus infinity. It's not the most standard one, which is Fourier, but is a good basis to expand things. Okay? And it's the sum of all projection on all things is just one. Now, let me give you, in fact, now a couple of examples where I immediately use examples in which the sum is really an integral. Okay, so suppose that the operator is just x, position operator. So instead of a, I use x. Now, you know that the eigenvalues of x are just continuous, position on any possible point. In principle, the projection operator on a certain n now has to be interpreted as a projection on a certain x, okay? Which reads in the Dirac notation x, x, okay? If this is in 3 dimensions, you should put a vector, otherwise it's just a point. All right? So this is the projection on a certain point. Now, what this becomes is now an integral. Okay? So integral over all position x of px, which is x, x, is equal to the identity. Okay? Now, for instance, let us take a state and write this as identity times psi, where we use this object. Now, this is nothing but the integral of x, x, psi. This is what? This is the component of the state at the point x. Now, we have already encountered it, in fact. It's our beloved wave function. Okay? So what we used to call the wave function at position x is nothing but the projection, the scalar product of the state with the eigenstate x localized exactly in position x. Eigenstate of position. Okay? A pretty singular object, you realize. Okay? It's, I mean, a delta. So it's not very physical. But the fact is that it's not very physical because, I mean, nothing could be in that state because it would have an infinite uncertainty in momentum. You cannot localize a particle with a delta. Doesn't eliminate it from the description. In the same spirit as plane waves are not normalizable, but still they are useful to expand any possible wave packet. Okay? So the localized states in positions are also not very physical, but they're useful to expand any possible state, okay, in this form. All right? Is this clear? Good. Now, there are other eigenstates that are particularly useful. For instance, if you take now momentum, another important operator. Then you might say, okay, then I have the projection or operator on a certain momentum p. Okay? Well, I'm calling here, you know that momentum has an h bar on it. Okay? Let me call it, so on a certain momentum h bar k. So let me use just k to label the momentum state. Okay? So these are eigenstates of momentum. You know what they are, by the way, okay? So you know that their wave function, so x k is equal to the plane waves. So e to the I k dot x. Let us use, in fact, the normalization 2 pi cubed. Okay? So this is the wave function of this state k, all right? The free momentum wave. Now, once again, you have the identity, so you can write one identity as integral over all k's of this thing, okay? So I can write a similar equation, but now the equation looks as follows. It looks integral over dk of k, sorry, it's too big here. K psi. Okay? So this is equally good as an expression for a state, but now obviously this object here is the wave function in momentum space. Okay? So rather than the wave function in position space. Now let's see, in fact, what is the relationship between these two ways of writing wave function, in position or in momentum. And we will discover a very entertaining thing that you know very well. So, for instance, let us look at this object here. K psi. Now, we use the trick of inserting identity. So I put an identity in the middle, K, 1 psi. But now, the identity, I write it rather than like this, I write it like this. Okay? So this will be what? This is just the integral in dx of k x psi. Do you follow me? Okay? Very simple. Now, this object here, I know what it is. It is the star of this object, because you see it's the scalar product with the opposite thing. So it's the star of that object. So this is equal to 1 over square root of 2 pi cubed integral in dx e to the minus I k dot x times psi of x. Okay? Is this clear? So the wave function in momentum space, apart from this factor here, is what I might call, in fact, let me call this object psi k. It's the Fourier transform of the wave function in x space. Okay? It's a matter of taste if you want to eliminate from the definition of Fourier transform the 2 pi cube square root. Okay? Perhaps particle physicists would include the square. I mean, if you include the square root of 2 pi cube, the definition of Fourier transform and inverse Fourier transform is more symmetrical. Otherwise, one appears without 2 pi cube factors, and the opposite that you can write in a very simple way. Okay? You just do the opposite route. You take this. You insert now this, because you can put the identity in here. And this means integral in dk of x k k psi. All right. Now, this is 1 over square root of 2 pi cubed e to the I k x. This, you see, is, I insist in calling, for instance, the Fourier transform only this and not the square root. So this is equal to the Fourier transform divided by another 2 pi cubed square root. Okay? So if you put all the 2 pi in common, I get dk 2 pi cubed without square roots, because there are 2 square roots. And here I have e to the I kx, and here I have psi of k. Okay? So hopefully this reminds you of Fourier transform. So psi of k is the Fourier transform of psi of x, and psi of x, which is this, is the inverse Fourier transform of psi of k. Okay? You see here a characteristic 2 pi over cube and nothing here. So you can be more democratic and put the square root here and the square root there, as you wish. Yeah?
I thought like, okay, the square root of 2 pi cubed is the volume for a microstate in phase-space, right? That's why they put...
Well, in fact, I like more this, because this is much, in some sense, much simpler. If you remember our discussion about quantizing plane waves in a volume L cube, okay? You remember that the different K's were essentially separated by 2 pi over L, okay? So in some sense, the volume in K space is 2 pi cube over L over the volume. And therefore, for instance, something like 1 over L as sum over K becomes immediately integral in dk over 2 pi cube. Okay? In other words, there is a 2 pi cube here if you want to obtain just the integral, or vice versa, if you want just 1 over L cube, you put the 2 pi cube there. So whatever, okay? It's a matter of really convenience. I like to have the 2 pi to the dimension of the space underneath K, but there are people who like more the square root there. So it's a matter really of redefining what you mean by Fourier transform up by a coefficient. Okay, so is this clear? So you see this identity allows you to write inverse and direct Fourier transform in a very simple way. So if I ask you what is the wave function in momentum space, now you should be able to answer, right? So what is the probability of finding the particle in a certain momentum k? What you should do is to calculate psi of k. So take the Fourier transform of whatever wave function I give you, and take the square modulus of that. Now, in fact, we'll discuss more about probability of finding things in certain. So this is the next topic that we'll tackle. Is this clear? As an example? Now, let me return for a second to a more general framework where I have all these things specified. So suppose that I now use a generic operator A, and I want to write, therefore, projection in general. The single projector will be on a certain state AN on a certain level I associated to that AN. So this is the single projection operator. And the identity is nothing but summing over all AN and summing over all I from 1 to the degeneracy Dn. Okay? So this is the new identity, more in general. So before I was writing just sum over n of phi n, now I am more detailed and I say, no, it's a sum over all the eigenvalues and sum over all possible degenerate states that have that eigenvalue. This is clear to everybody? Just a more, heavier notation, but a bit more detailed in some sense. And so, for instance, a state, I write it as identity times the state. I can write it using now this form of identity, sum over all possible eigenvalue an of the operator A. Notice, this is an operator that I decided, okay? The state is whatever it is. I decide an operator, Hamiltonian, angular momentum, x, p, whatever, okay? An is a sum over I from 1 to dn. And then, obviously, there is phi ani, phi ani psi, okay? So this is the amplitude of the state in the given eigenstate ani of the operator A. All right? So unlike, the previous thing here was that the state was integral in dx of x psi. So this was the psi of x. So this is the analog of the psi of x. Are you seeing it? It's just the amplitude of having the state in that precise eigenvalue an and index I. Okay? Is this clear? Now, exactly in the same way as the integral over all points of psi x modulo square is 1, you can prove in a very simple manner that in a sense, since the state is normalized, since psi is equal to 1, it's very simple to prove that the sum of all the square of those coefficients, modulo square of those coefficients, must be 1. Okay? So in other words, 1 is equal to the sum over all an, sum over all I from 1 to dn of the modulo square of those coefficients. Okay? This is a basis. Therefore, all the individual components in the basis, you take the square, must sum to 1. Is this clear to everybody?
In this case, phi represents
Phi, this one? Eigenstates of the operator A, which I'm not specifying to you. It's an Hermitian operator. Okay? I'm just generalizing what I was doing there in pretty much detail for x and p. Okay? For instance, this might be the harmonic oscillator Hamiltonian. Suppose that I have a system in 1D, but not necessarily an harmonic oscillator. Just a system in 1D. Now, I can use as a basis for that one-dimensional space the harmonic oscillator eigenstates. Okay? So this is the harmonic oscillator, Eigen-Hamiltonian, and these are the Hermite polynomials times e to the minus times the Gaussian. Okay, this is a basis. Yes, absolutely. I mean, to obtain all these things, I must use an orthonormal basis. If I take an arbitrary basis, there would be numbers around. Yeah. But I said, if they are not orthogonal, you can make them orthogonal by just finding appropriate combinations. Okay? Yes, I assume that I have performed an orthonormalization. You know that if you have a given basis, I can perform a Gram-Schmidt orthogonalization. I take the first, then I take the second minus the projection on the first, zack, and I rescale, and then I take the third, and I subtract the projection on the thing, and I rescale. Okay, this is a way of, for instance, producing a nice orthonormal basis out of an arbitrary one if you have degeneracy. Okay? So I can always do that, and I assume I do. Otherwise, the formulas are more complicated. Scalar products do not involve always a simple delta. They might have different numbers, and this is not very nice. Okay? But apart from that, please just work with a little bit of abstraction. So these are states specified by me because I like some Hermitian operator. And in this basis, you can still write an identity, and therefore you can still write an expansion for the state now, not, for instance, of this type, so not in terms of wave functions in real space, but in terms of wave functions in these labels in some sense. Okay? They tell you what is the amplitude for finding, for instance, the state in a certain eigenvalue an of the harmonic oscillator, for instance. Okay? So what is the amplitude of that state in the Hermite polynomial number 3 times the Gaussian? What is it? It's a scalar product. It's this. Okay? Take any function. I can ask you, what is the amplitude of this function on, say, the ground state of the harmonic oscillator? You multiply by Gaussian, you take the integral, and you tell me 0.2. I don't know. Okay? Is this clear? All right? So these things here are scalar product of, for instance, you can, by the way, if you want to be explicit, insert an identity here in this form. So these are nothing but integral over dx of phi an I x x psi. And this is what? This is equal to the wave function, okay? And this is what? This is equal to the star of the wave function an. And we recover again the definition of scalar product we had before, okay? When we wrote it, we directly wrote it in x, okay? But in more abstract terms, in general, is a scalar product in this space that might not really be spelled out in wave functions of x. In fact, this is very useful because sometimes wave functions are not functions of x. When we will encounter spin in a very short while, spin is not a wave function in x in the ordinary sense. It's a state, however, a state in the Hilbert space, okay? But it's slightly more abstract in some sense. And this is the reason why it's better to really eliminate this burden of having always to have a psi of x. Because x is not always there for you, okay? The spin is not psi of x. So abstract vectors like this are a bit better. But I didn't want to introduce it from the beginning in a very abstract way. So I wanted to start slowly with just ordinary things that you know, and now you see that you can think of those same things in a more general setting. Okay, so is this clear? If it is not clear by analogy, there's nothing better than just verifying it. Okay? Shall we do it? Perhaps you are a little bit confused. Say, how do I know really that the square of these things should sum all to 1? It's very simple. So take this expression, which I think you understand, right? This is the identity written as a sum of projectors. Now, just take the scalar product of psi with itself. We know that this should be 1. Okay? So you write this as sum over an, sum over I of this object, so of phi an I, phi an I psi. And then on the left, you write a similar expression, but remember that when you have labels like this, you should just use other labels. They are just labels on which you sum. So don't write the same labels. So I write sum of a n prime, sum over I prime from 1 to d n prime. And then I have, again, the star of this, okay? So phi a n prime I prime psi star, and the bra of this, so phi a n prime I prime. Did you follow? Now, since the basis is orthonormal, you see how useful it is. This is a delta n n prime and the delta I prime. Okay? Therefore, this double sum is really a single sum. Okay? So I write it as equal to sum over an, sum over I from 1 to dn. And then look what I have. So this has become a 1. I have this times its very same star. Okay? So the modulus square of this, phi an I psi. Okay? And this is what I wrote here. Okay? So it's a very simple consequence of the fact that the states are normalized to 1. The square sum of all the coefficients on all states of the basis are just 1. Okay, until now this was a little bit of formal machinery, but probably known to you, or in any case not very detached from what you know. Now I'm going to introduce a couple of things that are kind of basic postulates of quantum mechanics, and some of them are not particularly easy to justify. I mean, they are justified by the fact that nature seems to do that, okay, in some way. So, so to be ready with this proof, I think I should erase a few things. This I leave. Okay. Okay, suppose I take a state, I have a certain state, psi, prepared in some way, and I decide to measure with an apparatus to measure some observable. Measure A. For instance, an energy or whatever. Now, the apparatus, I don't specify how it is. It's not of my business at this point. The first basic thing that quantum mechanics tells you is that if I measure A, I will always obtain, in any experiment, one of these numbers. Okay? For instance, if I measure L square, I will always obtain one of these numbers. So 0, 2, 2 times 3, 6, okay? Not 5 or not 4. Only one of this, okay? So measure A, then I obtain as result of a single measurement one of the AN, okay? One of the eigenvalues. Another thing that quantum mechanics tells you is that if you repeat, okay, repeat measurements of A, generally speaking, you obtain different AN, okay? So the first time I measure J square, I obtain, for instance, 2. The second time I get 0. The third time I get, what was the other? 6, okay? I obtain, in general, different numbers. And what the theory tells you, and in this sense, this is probabilistic, because everything we have said until now, the evolution of the Schrödinger equation is very deterministic. It's a differential equation, okay? Nothing really is left to chance. But if I measure something, I can obtain one of the eigenvalues, and in general, it's not always the same. But the probability of obtaining some eigenvalue AN, guess what the theory tells you is proportional to? Now, I have already told you that the probability of finding the particle in X was psi of X modulo square. Now let us extend this. The probability of finding a certain AN is equal to this, okay? So this is the sum over I from 1 to dn of phi ANI psi modulo square, okay? In other words, the sum of the squares of the psi in that subspace it tells you how much of psi is really in that subspace, okay? After all, this is very reasonable. You see, this is PAN. So from this equation, you immediately see that the sum of PAN is 1, okay? So this is a very reasonable probability in some sense, okay? In any case, this is one of the basic postulates of quantum mechanics, that if you perform repeated measurements and you accumulate histograms, okay? So for every value of AN, you keep counting occurrences, then the probability in the end of getting a certain eigenvalue will be just given by this expression if you have a way of calculating it. Yep.
Is it always the sum? I mean, for instance, if we take particles which are not distinguishable or something, I don't know.
This is a more complicated thing, okay? Then you have to really, in any case, all I have said here is pretty much general. In fact, I'm working really with states that I'm not really, it's not necessary to say that these are single particle states, state of a single particle. All I'm saying is pretty general. However, if you have more than one identical particle, so several electrons, then the states themselves are written in a very special way. They have to be properly anti-symmetrized, okay? So there is more complication in the way you write states. But if you work at this very abstract level, okay, everything I said is not just for a single particle. It's very, very general, to a high degree of approximation of what I'm saying, okay? So these formulas indeed are there in more abstract and more general settings than just a single particle in a potential that we have considered from the beginning of the course, okay? All right, so This is what the first part of the story, not the only. The story then goes on as follows. Suppose that I measure A, a single measurement, I obtain AN, okay? After that measurement, so I measure A, and I obtain a certain AN. I know that if I do it several times, the probability which I obtain this is PAN. But for the time being, let me just assume that I obtain a certain AN, say 6 here. Then the theory tells me that after measuring, the state changes. And changes in a very abrupt way. Okay? Unlike the deterministic Schrödinger equation, this changes in a brutal way. So you see, the state before was sum of all AN, sum of all I within the same AN of these things. After, becomes very, very simple. Becomes sum over all I compatible with that AN of phi AN I, phi AN I, psi. In other words, you have kind of projected, you have kind of filtered the state with the specific AN you have measured. Obviously, you might say, hey, but if this was normalized when summing over all AN, then if I take only a single AN, this will not be normalized. In fact, in general, here there is a new normalization constant that I have to add. Okay? So the state is like first generic superposition, then I measure, I get AN, tack, collapse on the given direction AN. You see? The result of the measurement essentially collapse the wave function exactly in that subspace. I don't know, obviously, which state. I mean, it's in general still in a mixture of, no, not mixture, not me used, in a superposition of several I's, okay? So the different degenerate states are not touched in this scheme. Only the different eigenvalues, okay? Now, you realize that this is a very subtle thing, okay? And people have discussed a lot how comes that, I mean, how really a measurement that is putting the system in an apparatus that has some classical, obviously, degrees of freedom, your eyes, I mean, some knobs, some things that point, how is it that really this very strange collapse happens? Don't ask, okay? Don't ask such questions. There are books and, I mean, 100,000 pages have been written discussing why so, why not so, and so on. There are several interpretations. We don't care, okay? Just be brutal. We don't care. This is it, okay? This interpretation has survived many attempts, many of disproving it, I mean, many experiments, and for us is the truth. Don't even doubt it. Okay. Now, you see, however, an immediate consequence of this too. If I now perform a new measurement, so I measure A, I obtain AN. Now, immediately after, I measure A, but now on the state psi prime, not A, not psi. So here I was measuring A on the state psi. I got some AN. Here there is the collapse, okay? And now I measure A again on psi prime. Can you tell me, according to the first, what I should obtain? What value of A should I obtain?
I can be from those degenerate states.
They all have the same AN. I'm not able to discriminate the different AN because I just measure A. So I've not measured anything else than J squared, okay? I'm not able to discriminate which of the eigenstate of J squared is really occurring there. It's just...
A times P of A.
Huh?
A times P of A. Okay,
No. P occurs only for probabilistic way of obtaining AN. But now I tell you, this is a single measurement, okay? So it's a single, so no PA. This is not important. It's a single measurement. I obtain first AN. I collapse the state, and I measure immediately after A again. What do I obtain?
AN times that prime.
AN times?
That prime.
No, I told you that I can obtain only eigenvalues of A. So AN times what?
Okay, the state side prime.
A result of a measurement is a number, not a state. AN.
Yeah.
There's nothing else I can obtain, okay? According to my first thing, I should obtain one of the eigenvalues. But I look at the state, the only pieces, okay, which are contained there are pieces with AN. So when I measure, in fact, measuring is like applying the operator AN in some sense, okay? And you see that I always get AN, nothing else. There is only that piece of wave function there, okay? So I obtain AN now with certainty, okay? So with probability 1. All right? So the first time I obtain AN, and if I repeat this first measurement, I would obtain AN with a certain probability Pn. But if I do 2 measurements in a row, if I obtain AN in the first, the second will be AN for sure. All right? Not another AN prime with probability AN prime. All right? So the collapse implies that the second is guaranteed. Okay? Yep.
What if we have a system which is a system which contains no identical particle? Can we measure the same particle each time, or can we measure?
The question is, I don't know if I understood correctly, if I have a system of many particles, not identical, can I make the same particle? This is a question for, first of all, is a question for an experimentalist. It should be more detailed. I mean, if an experimentalist tells you, I'm measuring this, you can ask him, how do you measure this? Okay? I really don't know, in principle, how to measure an arbitrary operator. I mean, what the detector I should prepare. Okay? This is somehow something that the ingenuity of the experimentalist has to sort, okay? But certainly there are certain things. For instance, if A is an energy, measure energy, okay? Measure the energy, I can get a number. This number should be this, okay? Well, again, if I measure repeatedly with a certain probability, if I get a certain energy, after that, that is an eigenstate of the energy with that value. If I remeasure it, I obtain same number with certainty. Okay. Suppose hydrogen atom, okay? Suppose that rather than starting from the ground state or the first excited state, I start from a state, okay? A certain superposition of all possible state. I measure the energy and I get -1 Rydberg. I measure it again from the same state. Next time, I will not obtain -1 Rydberg. I might obtain -1/4 of a Rydberg. Okay? So if I collect the probabilities, I will be able to essentially get a complete picture of the state, saying this state has a certain probability of being in the ground state, a certain probability of being in the first excited state, and so on. Okay? But the important thing is that if I first measure -1 Rydberg, and immediately after I measure the energy again, I will obtain -1 Rydberg, and not -1/4. All right? Because the state has changed as a result of my measurement. Okay? This is all I want to tell you. Don't think of more sophisticated schemes. You should ask an experimentalist, okay? Not me. I don't care.
No, if the state has changed,
the measure changes. And it changes in the way that before I had only a probability of getting some number. Now I have a certainty. Is this clear? I only want to make clear this very little thing. Not how can you possibly conceive an experiment to measure whatever you want on the 15th particle of your very complicated system. I couldn't care less. Okay? I want to make sure that you understand that if I have a state, so let me just make an example. Your state, okay, was some preparation that I don't even want to know, but according to the theory, might be a superposition of the ground state of the hydrogen, so the state with n equals 0. Then there might be a state with, say, n equal 1, L equal 0, the 2s. Sorry, this is n equal 1. So this is the 1s. Let me use just 1s, 2s. Then there might be 2p component, whatever, okay? Here there is some coefficient, I don't know, 1 over square root of 2, plus here there might be 10 to the minus 4, and here there might be other numbers, okay? Now, I measure the energy. I would obtain minus a Rydberg. Next time I measure an energy, I might obtain minus a quarter of a Rydberg. I collect all the results of my measurements, and I notice that half of the time I get minus a Rydberg. But 1 every 10 to, well, maybe I made it too small. 1 every 10,000 times I obtain indeed minus a quarter of a Rydberg. And a few other times I obtain other values, okay? But for any single measurement, if I obtain minus a Rydberg, and on that very system, okay, I measure again the energy, okay, on that system, not on this, on that system, which is this. It has changed, okay? It's a different system, all right? I measure an energy, I change the system. I measure again, I obtain a Rydberg. Is this clear? Measurement changes the system. It's written here. Okay? It's not the same system any longer. If I want to repeat my experiment, I should throw away this and start fresh from another state prepared in exactly the same way. Okay? And I repeat another measurement. Is this clear? Okay? Now, yeah.
Because we are doing now for A, that which represent an observable. The other observable, another observable of the same system.
Okay, she's asking things about two different observables, which was indeed the next thing I wanted to say. Okay, so suppose that you have a state, you measure A, you get AN, and now you measure another operator, B. Okay? So on this state, I measure another operator, B. What do I get? Well, an easy answer is one of the possible eigenvalues of B, for sure. But there is a crucial difference depending if A and B commute or they do not commute. Because if they commute, you know that they have a common basis of eigenstates. And in particular, you remember that A and B essentially have common subspaces which will not scramble between each other, okay? So if I measure B, which is compatible with A, in other words, that commutes with A, I will obtain one of the eigenvalues of B that stay in that subspace. Remember that I have, okay, if I draw the matrix of A, I will have a certain block associated with the eigenvalues an, all an, of dimension dn, dn times dn. Okay? Now, the first measurement tells me that I'm going to be in one of the states belonging to that block. Now I measure B, and B doesn't scramble that. Simply, there is a way of writing those states, and I will obtain, in general, different eigenvalues of B. Okay? So I can obtain one of the eigenvalues of B, which belongs, however, to that subspace. All right? Now, you realize that if I measure, and this will obviously collapse the wave function to a psi second, depending on what eigenvalues I get. If I measure A again after B, since this has not changed where the state was staying, it is still in the same subspace, I measure A, and I get an again. Okay? So you see, I obtain the same number even if I measure another operator, not just the same, another operator, as long as the other operator is commuting with A. Is this clear? For instance, I measure J square. I know that the state will be in a certain projection of states that all have the same value of J square, for instance, 6. Okay? But I know that there are, corresponds to J equal 2, so I know that there are 5 states that have the same value, 6. Now, I don't know which one of those 5 I'm ending up. Then I measure something. For instance, I measure LZ. So B would be, B is LZ. And I get some eigenvalue, for instance, -1. Then I measure J square again. What I get? I get 6. Because that -1 has not changed the content of J square. It simply refined my information about the state. It's telling me that not only the angular momentum is J equal 2, but the component along Z is -1. Now I measure J square again, and I find 2 again. Or in other words, J square equals to 6. Okay? I'm not scrambling that piece of information by measuring a compatible observable. I'm just refining it. On the contrary, if I measure after, for instance, LZ, I measure LX, then they do not commute. And I in general rewrite all these things into the basis of eigenvectors of Lx, which is not common to the basis of eigenvector of Lz, and everything is scrambled. So next time I measure Lz, I might change things. All right? So be just aware that the process of measurement has a few things, like probability for repeated measurements, collapse of the wave function, certainty if you measure the same thing after collapsing, certainty if you have compatible operators. Otherwise, every measurement is a new measurement. All right? If the two do not commute. So with this, I would close this page. Please try to just think of this, because it might be useful in several occasions to have clear in mind. Yeah.
Does it mean that if we measure B, in this case, after measuring A,
Yeah.
certainty, we will have a certainty in our second measurement?
Yes. Yes. The question is, if I measure A, I get some number. Then I measure B, which commutes with A. I get some number for B. Then I measure A again. I get the same number as before. I measure B again. I get the same number for B as before. Because neither of them can change the result of the previous thing. Okay? In some sense, for instance, in this example, I had states. I had 5 states. They had different, same value for J square, but different value for Jz. I measure a Jz, which could be plus 2, plus 1, 0, minus 1, minus 2. Suppose that I measure minus 1. Then I measure this again. I'm sure I'm still there, and I measure 6. And if I measure again Jz, I'm not going to exit from here, because the state has been collapsed now to the very single state, eigenstate of both, and I get 6 for here, and again minus 1. I can measure it 100 times, always these two numbers. Because now I know I have a common eigenstate of both, which is never projected, never collapsed. I mean, it's confirmed every measurement. All right? Okay. Now, if this is the probability of getting a certain outcome for the measurement of A, you can certainly collect the numbers of your experiments and define, for me, the average. Okay? The average would be sum over n, an, times the probability of getting an. Okay? Now, it's a simple algebra. Well, it's kind of late. That will show to you that this is exactly the same thing as psi A psi. Okay? The simple algebra goes through essentially using this expression for psi, both here and there. The beauty of it is that it involves eigenstates of A. Therefore, when A acts on this object, it gives you immediately an. So it gives you this. On the other hand, this object here, with its partner on the left, has a delta function. So there would be a double sum. But once again, as before, there is a delta function. Okay? And from the delta function comes the square of this, pretty much as we have seen before, for proving that the sum of this thing was just 1. Do the same, very same algebra, and you discover that. So after all, what we did before was this. Psi equal to 1. Now we put A, but A has a very, very simple role. It just produces for you, pop, out of nothing, an. There. All right? So same algebra, similar algebra, and you get this. Okay? So what we insisted in calling expectation value of psi now has a very obvious meaning, is what you measure on average. Okay? Notice that in each single measurement you measure an, not the average. This is a very important distinction. Okay? You know that thing about eating, I don't know, a chicken. So if I eat a chicken, you eat nothing. On average, we have eaten half. Okay? No, these individual measurements, okay, are either 1 or 0. Okay? Not half. Okay? So these are averages, which are, however, not representative of measurements. Yeah.
What is the form of the coefficient that you put expression giving the measurement, the state after the measurement?
This one?
Yeah.
Oh, just 1 over the sum of the squares of this restricted to I. I mean, you pretend that this is still 1. Okay? So you can prove that this is equal to 1 over the square root of sum over I, the modulo square of phi a n I psi. Okay? In other words, the PA, 1 over square root of PAN is what you get there. Okay? Okay, now, not only you can measure expected values of an, but you can collect your measurement and calculate the square of your measurement and measure, therefore, an square averages. Okay? When you measure something, you know that you can collect histograms of the values and of the square of the averages of the values, and these are useful to obtain deviations, standard deviations. This is just ordinary statistics, nothing really surprising. Now, you know by the same, very same proof that this is just a square psi. because a square is, I mean, acting on phi n produces a n squared. Okay, same algebra. And therefore, you know that the standard deviation of the measurement of A, or if you want, the uncertainty, is equal to, or the uncertainty square is equal to psi A square, psi minus psi A psi square. Okay? Which you can prove is also equal to psi A minus average of A squared psi, where this average is just this. Okay? Which shows that this is a positive definite quantity. From here, it's not immediately clear. I mean, there is a negative sign, but this is always greater than this. Okay? And you can prove that this is equal. All right. With these very simple formal tools, you can, for instance, prove, okay, and I give you as an exercise 7.2 in this notes, the following thing. If you have two operators, A and B, and you calculate the uncertainty in A, in your outcome, and the uncertainty in B, then the uncertainty in A times the uncertainty in B should be greater or equal to 1/2 the expectation on psi of the commutator of A and B. Okay? You can prove this by a very simple, well, very simple. It's a kind of, you know the theorem, how it's called? Schwarz, Cauchy-Schwarz inequality. Okay? By application of that, you can prove this, which tells you, reinforces what I was saying. If these two objects do not commute, this quantity is necessarily different from 0, positive. So the product of the two uncertainties has to be finite. You cannot specify both simultaneously in an arbitrary way. Okay? So either you specify, well, A, but not so much B, or vice versa. I mean, you have already seen this. Is Heisenberg uncertainty principle. If this is X and this is P, the commutator is just I h bar, and you know that this number is just h bar over 2. Okay? But it's more general. And in particular, you notice that if the two operators commute, then this is 0. You can measure at the same time with infinite precision two commuting operators. For instance, I can measure with arbitrary precision J square and Jz, because there is a state that is common eigenstate of both. Okay? And I can, by repeated measurement, just collapse everything into that state, arbitrary precision. All right? And I think that we are quite tired for today.